Good day, everyone, and welcome to the start of our lesson on AVL Trees. My name is John Benedict C. Del Cruz, a proud member of Group 2, and today I'll be continuing our discussion on Unit 6, Nonlinear Lists with a focus on the AVL tree. But before we dive in, let me ask you a quick question. Have you ever wondered how AVL trees came to be? The AVL tree is named after its two Soviet inventors, Georgy Adelson-Velsky and Evgeny Lanzis. They introduced this data structure back in 1962 in their paper titled An Algorithm for the Organization of Information. This marked the birth of the first balancing binary search tree ever invented. So what exactly is an AVL tree? An AVL tree is a self-balancing binary search tree, or BST for short. Like any BST, each node has a left child with a smaller value, and a right child with a larger value. But here's a twist. An AVL tree adds a balancing mechanism to keep a tree's height as low as possible. This ensures that operations like insertion, deletion, and searching all happen efficiently in big O of log n time. Now, how is it different from a regular binary search tree? While standard BSTs can become unbalanced over time, especially with poor insertion orders, AVL trees have a built-in balancing rule. After every insertion or deletion, they automatically adjust themselves using rotations, either single or double, to stay balanced. Let's summarize the key differences. AVL trees maintain balance, keeping their height as low as possible. They perform rotations after insertions or deletions to preserve this balance. On the other hand, regular BSTs don't rebalance themselves, so they can become skewed or inefficient over time. Thanks to their balancing property, AVL trees consistently deliver fast performance across operations, with time complexity of big O of log n. Now that we know AVL trees are all about balance, let's talk about how that balance is actually measured. Every node in an AVL tree has something called a balance factor. This tells us whether a node is balanced, leaning left or to the right. The balance factor of a node is calculated using this formula. Balance factor is equal to the height of the left subtree minus the height of the right subtree. Some references may flip it around as height of right subtracted by the height of left, but either way, what matters is the difference between the two. Now here's how to interpret the result. A balance factor that is equal to 0 means the node is perfectly balanced. A balance factor that is greater than 0 means that the node is left heavy. And a balance factor that is less than 0 means that the node is right heavy. But here's the crucial part. If a node's balance factor becomes less than -1 or greater than 1, it means the tree is now imbalanced. When that happens, the AVL tree automatically performs a rotation to restore balance and keep operations running efficiently. Now let's move on to how AVL trees maintain balance through rotations. There are two types of rotations, single and double rotations. Let's start with single rotations, which are used in simpler imbalance cases. Left rotation is needed when we are presented with a right-right case. This happens when the node becomes right-heavy, and its right child is also right-heavy. In the left rotation, the arrangement of the nodes on the right is transformed into the arrangements on the left node. Imagine we have the situation A, B, C. To fix this, we must perform a left rotation rooted at A. This is done in the following steps. B becomes the new root. A takes ownership of B's left child as its right child, or in this case, null. And then B takes ownership of A as its left child. The tree now looks like this. As for the left-left case, a right rotation is required to maintain balance. This happens when a node is left heavy and its left child is also left heavy. In right rotation, the arrangement of the nodes on the left is transformed into arrangement of the nodes on the right. Imagine we have the situation A, B, C, which is similar to what we encountered a while ago. To fix this, we will perform a single right rotation rooted at C. This is done in the following steps. B becomes the new root. C takes ownership of B's right child as its left child, and in this case, that value is null, and then B takes ownership of C as its right child. The tree now looks like this. However, sometimes a single rotation isn't enough. That's where double rotations come in. These are used for more complex imbalance cases, such as the left-right and the right-left case. The left-right case is when the unbalanced node is left heavy, but its left child node is right heavy. To fix this, you must perform a left rotation on the left child, which is F on this situation, then a right rotation on the original unbalanced node, which is E according to the figure we are observing. Moving on to the second double case, the right-left case, which occurs when the unbalanced node is right heavy and its right child node is left heavy. In this case, we first perform a right rotation on G, the right child, and then a left rotation on E, the original unbalanced node. These rotations are the key to maintaining the balance of an AVL tree after insertions and deletions, ensuring that the operations remain efficient at big O of log n time. Now let's take a look at the key operations you can perform on an AVL tree, including searching, traversing, inserting, and deleting nodes. In an AVL search operation, nodes of the AVL tree are compared with the node that has been requested. It is the same as in binary search tree, as the following steps are followed. First, start from the root. If the key is smaller, go to the left child. If the key is larger, go to the right child. If they are equal, then that means the key has been found. In a traversal operation, one can use the standard binary tree traversal techniques, such as the depth-first traversal or the breadth-first traversal. The depth-first traversal technique explores as far down a branch as possible before backtracking, and it has three common variations: the in-order traversal, the pre-order traversal, and the post-order traversal. As for the breadth-first traversal, this technique explores every node at a given level before proceeding to the next. Essentially, it visits a node from top to bottom and from left to right by level. Moving on, when the insertion operation is carried out, a node is inserted at a leaf. Consequently, the AVL tree's height must be updated, and rebalancing through rotation may be required if the node is unbalanced, where the balance factor is greater than 1 or less than -1. Lastly, during a deletion operation, a node to be deleted must be located, and then the AVL tree's height must be updated. After the deletion, if the AVL tree is unbalanced where the balance factor is greater than 1 or less than -1, rebalancing through rotation must be implemented. Once again, I am John Benedict C. de la Cruz, and that is all for our theoretical discussion.
So, good morning, guys. I am Braldi Mape, and today I'm gonna show you how AVL tree works. So first, I'm gonna give you an example on how to identify if it is a balanced tree or unbalanced tree. So first, let's say we have a node 10 and its child is 5 and 15, and 15 he has a left child of 12, and so 12 is the grandchild of 10, right? 12, grandchild of 10. So is this a balanced tree? Yes, it is, because um we'll we'll start from the bottom. So this one, it doesn't point to any node, so it has a zero balance factor. And 15 has one child and no child to its right, so it has a one balance factor. How about 5? So 5 doesn't have any children, so it has zero balance factor. How about 10? So balance factor is the difference between the height of its left minus the height of its right. So to balance the height of its left and height of its right is equals to, so height of its left, it has 1, right? 1. So we're gonna put 1. And height of its left, we have 1, 2. So we're gonna put 2. And we're gonna get the difference of it. So it is either 1 minus 2 or 2 minus 1. It doesn't matter really, because on AVL tree, the balance factor must be 0, 1, or negative 1. So it has a negative 1 balance factor. So this means this tree is a balanced tree. So next, how about this one? Um, we have 5, 7, 8, 11. So is this a tree? It is, but it is not an AVL tree, because left because the left pointer of 5, it doesn't point to anything, but the right points to 7, and the right of 7 points to 8, and the right of 8 points to 11, right? So this is a tree, but it is not, it is an imbalanced tree, because first we're gonna get the height of the left of the root, which is 5. So height 0, because it doesn't have any node here. So height of the right, we have 1, 2, 3. We have 3. So 0, 0 minus 3, we have negative 3. But on an AVL tree, the balance factor of an AVL tree, it only must be 0, negative 1, and 1. Dili man siya negative, ang negative 3 kay wala man sa parameters of an AVL tree, the balance factor of an AVL tree. So it is not balanced. So it is unbalanced, because of its balance factor, which is equal to negative 3. Now let's move on. I totally forgot. Ang time complexity of an AVL tree is O log n, right? As I've mentioned, O log n. But this one, 3 siya, but when you traverse it, kay more na siya ON. More na siya linked list. Like, you have to go to 7 to 8 to 11 when you're gonna search for 11. More na siya ni traverse on a linear path. That's all. We're gonna have an example to help you understand how to identify balance and imbalance tree. So let's say we have a node here, 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 here. Is this balanced? So we're gonna check it out. So first, we're gonna identify the height of the left subtree and the height of the right subtree. So the height of the left side is 1, 2, 3. So we have 3. And the height of the right side has 1, 2. So 2. And 3 minus 2 is 1. It passes the parameters of being an AVL tree, which is this one. So how about this one? Um, hmm. We have a node here, a node here, a node here, here, a node here. Okay, how about this one? So to find the to figure out if it is a balanced tree, we're gonna start at the bottom part of the tree. If it is balanced, we're gonna find each of the nodes balance factor. So here it doesn't connect to anything, so it has 0, and also here 0, 0. So every leaf is or has a balance factor of 0. um Next is the balance factor of this node. It doesn't have a left child, so it has a balance factor of 1. How about this one? This one. So it is -1. Well, why -1? Because if you'll choose HL minus HR, you'll get -1. But if you go with HR minus HL, if you go with this one's gonna be 1, and this one's gonna be -1. So we're gonna follow some rules, like we have to be consistent on what we use. We're gonna use this one or this one or this one. It's totally up to you. So for now, we're gonna use this one. To further explain why -1, cause yeah, I mean, sorry, my apologies. So we're gonna use HR minus HL for this one, for this one, for this one, right? So HR minus HL, we're gonna, kailangan consistent para dili maglibog. Okay, guys. So the right, okay, we have 0 and not a 1 here, not a 1 here. So we're gonna put 1. 0 minus 1, -1. So that is why -1. So how about here? Okay. We have, so right, we have 1. So left, we have none. So 0. 1 minus 0, 1. So 1 on 1 here. So it is totally up to you kung HL minus HR or HR minus HL for the balance factor, guys. Balance factor niya. Okay, moving on. How about this node? We have HR, HL. So the height of its left subtree, it has 1, 2. And its height, so right, 1. So 2 minus 1, 1. So balance o siya guys. It falls under the parameters of an AVL tree. So moving on. How about the root? We have right, we're gonna find the longest chain, okay guys? The longest tree. 1, 2, 3. So 3. And for the left, we have 1, 2. So 2, 1. So 1 siya. Overall na tree 1. So it is an AVL tree. Okay. I'll give you an example of an unbalanced tree. So this is an example of an unbalanced tree. Let's figure it out its balance factor of each node one by one. Okay. So let's start from the last or the bottom node. So it doesn't connect to it doesn't have any children or child. So zero na siya guys. Also this one tulad sa kilid. This one, this one. All leaf has a balance factor of 0. Remember that. And this one, HR 0 minus HL, which is 1. So we have -1. Because HR niya 0, 1, we have -1. How about this one? We have 1 siyang right. So 1. How about siyang left? 1, 2. So we have 2. 1 minus 2. 1. -1. Sorry. My bad. So it has a -1. So balance siya guys. Moving on. For this node. Sa may right niya kasi left. So 1, 2, 3. So 3. Ngano man dili kini 1, 2. Ngano dili man kini? Because ang longest chain atong i-follow. 1, 2, 3. So it has 3 siyang sa iyang left here, left side, like 1, 1, 2, 3. 3 siyang left side, siyang right kay 1. So 1 minus 3, -2. So it doesn't fall on the parameter of being an AVL tree. Kaya ang balance factor sa AVL tree kay -1, 0, or 1. So -2 yung balance factor. How about sa kini yung node? So it has 1 siyang left. Since left man, so negative na, -1. Kay 0 man here. Kay siyang right, 0, 1. 0 minus 1, -1. How about the balance factor of its root? But the right side we have 1, 2. So 2. How about its left side? We have 1, 2, 3, 4. So we have 4. 2 minus 4 is negative 2. So as you can see, nasa negative 2 niya ang pwede sa AVL tree kay ang balance factor nga pwede ra kay 1, negative 1, 0, or 1. So now my 2, what are we gonna do with it? So we have to rotate. This is where rotation comes in. So we have 4 types of rotation and we're gonna discuss it now. So now we're gonna deal about the rotations of an AVL tree. So first we have right. Wait. Right. I mean right, which is a left or right rotation. So in left, it means we have an example of here, a node and a node here and a node here. Let's say this is a, from the example on the PPT, B, C. So to perform right rotation, it is called left because it is on the um, left side of A. So look, left. So that is why it's called left, or right rotation. So it must be rotated kay the balance factor of here is 0, right? And it has a balance factor of right, hr minus hl, and hr is 0 and hl is 1, so negative 1. So far balance pa ni here nga part, but here we have the right side, the left side, it is 1, 2, and 0 or none on the right side, so we have negative 2 or 2, 1. It depends sa pag-solve sa imong balance factor, but in here I go with hr minus hl. Here. Okay. So we have to do a right rotation in order for this tree to be balanced. So what are we gonna do is we will get B, or B will be the new root of the tree. So since the new root of the tree, so it is gonna be like this, B, right? It is B is the new root, but how are we gonna identify which goes left and which goes to the right? It depends. But I'm just using letters here for placeholder, and we're gonna have examples with values to help you understand. So we're gonna put A here, and we're gonna put C here, right? So this tree is now balanced because the children has 0 or the leaf has 0 balance factor, balance factor, wait, balance factor of 0, 0, and here we have 0 because 1 minus, because 1 minus 1 is equal to 0. So it is a balanced tree. So this is how the right rotation occurs. It rotates to the right, like it rotates like that to the right. Do you get it, guys? Hello, shit, hindi mo. So yeah. So how about we're gonna use values in order for you to help you understand. Kay maglibog ra kayo if placeholder guys, di ba? So we're gonna use values. So let's say we have 30. No, lang. We have 3, 2, 1. So what are we gonna do is rotate it to the right, and it is left because the root has a child to its left, and the child has a child to its left. So it is all on the left side. It is called left or LL. So we're gonna rotate it and to the right. So it is 2 now is the root, right? 2 now is the root, and what goes to the left and right. So as you remember, on a binary tree, the left side of a tree is the lesser value of the root. So 1 goes here, and otherwise on the right side. So this is now balanced. This is now a balanced tree because it has a 0 balance factor here, 0 balance factor here, 0 balance factor here, because 1 minus 1 is equals to 0. So that is how right rotation works. We're gonna continue with left rotation, or right, and now like complete opposite is right, which is left. So left rotation is right, like all of the nodes is on the right side. So for example, we have 10. 10. 1, 2, 3. So we're gonna rotate it to the left because unbalanced man a tree, as what I've said, 0 ang balance factor ani, and 1 ang balance factor ani, and 2 ang balance factor ani, because kanina itong i-follow. Right. Did you get it, guys? Okay, nice. So now we're gonna rotate it to the left, like that, for the tree to be balanced. So if we're gonna rotate it, we're gonna get the middle as the root, right? That's what I've mentioned. And of course, to the left, good ang 1 and 3. So this is a balanced tree na kay 0 here, 0 put here, 0 put here, 1 minus 1, 0. So this is how left rotation works. Okay, we have an example here for right rotation or left left. We let's say we input, 20 here. So we're gonna find where to put 20. So is 20 greater than or less than 60? Less than, so we'll go to the left. Is 20 less than 50? Yes. So we're going to the left aside. And less than, yes. Less than, yes. Na I node, connect, wala. So we're gonna input 20 to the left of 30. So is the tree balanced? No, right? Okay. Gapundok ang mga nodes sa left. That's why it's called left left. Pundok ang mga nodes here. So what are we gonna do is to rotate it to the right. So first is always remember to start from the bottom. And we're gonna figure out the balance factor. So first, 20 has a balance factor of 0, so it is balanced. How about 30? So it has a 1 here and 0 here. So we have HR minus HL. So HR 0 minus HL. So we have negative 1. So it is balanced according to AVL parameters. How about 40? So 40 has 0. So 0 minus 1, 2. So it has a negative 2. Oh no! Unbalanced na siya. So we're gonna rotate. Mao na nga tayong rotate because nakasugat tag unbalanced. So i-rotate na ni guys. So we're gonna do is unsa man ang new root sa kini nga subtree. 30, correct. So 30, and of course greater than 30 is 40. So here gets right. And 20 here. And kadayon to ang wala na balance. $60. Sorry for my handwriting, guys. Okay, I'm gonna minimize this. So rotate this to the right, and it will come to this. So after the right rotation, the tree is gonna look like this. Okay, now we're gonna figure out its balance factor asan. So mo ng algorithm sa AVL tree, guys, whether it's insert, deletion, and we're gonna delve deeper about that. So this is insertion now. When I said insertion, because I said we're gonna insert 20 and we're gonna balance it. So every time I insert that, we're gonna balance it kay AVL tree man siya. So now this is the new tree. Balance pa siya di. Of course, we have 1 here. 1 minus 1, 2, 3. 1 minus 3, negative 2. Negative 2. Balance factor is 60. So it is not balanced. How about 50? Balanced na ba? 1 minus 2. Negative 1. Balance na siya. So okay na ni. And kaning 60, kaning whole tree, kay dili pa daw balance because kapundok pa here. So what are we gonna do is find nasad a new root. So may new root ani. Here ta mag-focus. Since balance naman ni. And this one, okay naman na siyang order. So kanina to i-focus. Guys, okay, balance naman. So now, unsa may new root ani? It is 50. You're correct. 50. Wait. 50. This is the new root now. And what will be its children? So if we're gonna rotate it to the right, so this one, so 60 is gonna be at the right of 50. So this 60 will be the new child of 50. So 60. And this one, since okay naman ni, we're just gonna insert it to the left side of 50. So we're gonna insert it. After I copy paste. Paste. Okay. So okay na guys. So we have remaining nodes, which is 55 and 17. And what are we gonna do with it? Asa man ibutang? Of course, bawal man natin ibutang dire because they're greater than less than 50 raman. So we're gonna put it here. So what is asa man ibutang 55? Sa left side, okay, less than man. So 55 here. Sorry guys. I big space 55 here and 70 here. Complete na ba? Let's check. So 940, 920, 930, 950, 960, 970, 955. So complete na ni. And let's check if balanced ba. So first, start to here. So ang leaf kay 0 yun na. 0, 0, 0. And how about 30? 1 minus 1, 0. 1 minus 1, 0. So how about 50? 1, 2, 2. 1, 2, 2. 2 minus 2, 0. So Peter said 1, 2, 2. Minus 1, 2, 2. So 0. So this is a balanced tree na guys. This is balance. Yay! So now another example for left. So sorry. So it is left and right example. Left rotation example. Or right where right subtree becomes too tall. This one. Okay. So if taas na siya guys, we're gonna balance it. Okay, of course, obviously, di na siya balance sa visually speaking. So now we're gonna rotate it to the left, but we're gonna delete 20. So first, if we delete 20, so okay, let's delete 20. Wala na. Obviously, rotate kita sa left because the right subtree is too tall na. Obviously, dili siya balance. And now, dyan na siya balance factor of right 3 minus 0. So 3 yung balance factor, which is clearly not an AVL tree. So now we're gonna find the new root. So first, we're gonna start at the bottom. So 60, 0, okay pa. 50, right, so 1, okay pa. How about 35, 0, okay pa. 40, 1, 1, 2. So 2 minus 1 is equals to 1. So okay pa, 1, okay siya. How about 3? Obviously, wala. Na-mention to na ako ganina. So 3, we're gonna rotate it to the left. So if we're gonna rotate it to the left, 30 now becomes the child of 40. So 40 now is the new root. So 40, wait, 40 now is the new root. So its child is 30 and another child for 50, and we're gonna add 60 here because as what I've said, okay naman diri nga subtree, like okay na siya. So how about 35? Where asa man ang 35? Obviously dili here because less than 40 man siya. Only greater than 40 can go to the right portion of 40. So 30. So here ba or here? Since it is greater than 30, we're gonna put it to the right. So let's check. 0. Okay. Leave man siya. Right. So 1. Right. 1. So 1 siya. 1 ang balance factor here. 1 balance factor 0, 0. How about here? 1, 2. Siyang left 2. 1, 2. Siyang right 2. 2 minus 2, 0. Which is an AVL tree. So this is correct. So always remember so when you insert or delete an item, you must the program itself must adjust for it to be balanced. So when you add a node, it rotates to its tree subtree if it is unbalanced, and rotate na sad, and so on until the full tree itself is an AVL tree na balanced na gid siya. As well as deletion. If you delete, let's say 50, so of course 60, if you're gonna delete 50, 60 is gonna be here, but it is still balanced. Yes, because 1 na lang here minus 2, which is negative 1, and it still passes the parameters of being an AVL tree. So we're gonna move on to left-right rotation. So now we're gonna proceed to left right rotation. So it goes the same as right and left rotation, but the rotation happens, I mean, like in a one tree, a tree must be rotated left and right in order for the tree to be balanced. For example, we have three, and we're gonna put it to the 10, 1 and 2. So as you can see, left, right. So we're gonna rotate it to the left first. So asa man to rotate, asa man una. So first is always remember to start at the bottom here. So obviously this sub tree is okay, but we're gonna rotate it to the left because it is really unbalanced. Look at, on the left side we have 2, on the right side we have 0. So the balance factor of 3 is -2. But this one, it has a balance factor of 1. So this is balanced, but this is not. But we have to rotate this as well in order for this tree to be balanced. So first, we're gonna have, or we're gonna rotate the first. We're gonna rotate this to the left. To the left. So if we rotate it to the left, 2 now becomes the child of 3. So 3, 2, and 1. So we're not gonna put 1 here because it is less than 2. So here. So what you can, so on sa inyong nakita guys, familiar, right? So mura siya left left. That's left left. So we're gonna do a right rotation. So we're gonna rotate it. We're gonna rotate it to the right na side, but the new root is 2, which is this one. The new root is 2. So if we're gonna rotate it, 2 now becomes the new root, and what is greater than 2 is 3, less than 1, right? So is this balanced? Yes, it is balanced because 0, 0, we have 1 minus 1, we have 0. So this tree is now balanced. So as you can see, we first start from the bottom, and now we can see now left here. So we're gonna do a right rotation, and after that we have this tree. We have left rotation and a right rotation. Okay. So now let's proceed to right left. So let's have the same example. I mean, not the same, like just the numbers. 1, 3, 2. As you can see, we have right, right, left. So we're gonna first watch, or we're gonna look for its balance factor. Balance factor of 2 is 0. Balance factor of 3 is -1, because 0 minus 1, -1. What here? Balance factor is 2. Okay, you're correct. So as you can see, 2 may balance factor. We have to rotate it in order for it to be fully balanced. So first, we're gonna rotate it. We're gonna look at its its bottom node. So it is okay, it is balanced. Here it is balanced, but here it is not balanced. So first we have to rotate this node in order to have, in order to fully, what do you call this, fully balanced. Because if we're gonna rotate it, to the right, we're gonna have like right, and 3 is gonna become the root. So 2, 1, which is obviously wrong. So dealing on that, guys, we have to rotate it following the rules of a binary tree. So first we're gonna rotate this one. We're gonna rotate it to the right. If we're gonna rotate it to the right, we have 2 now becomes, rotate it to the right. 2 now becomes the child of 1. And now asa na butang 3? 3 here. No, it's wrong because it is greater than 2. So to the right. So kung saan sa inyo nakita, guys, it is right. The right subtree is taller than the left subtree. So we're gonna do a left rotation. If we're gonna do a left rotation, 2 now becomes the root here. So 2, and we're gonna put 3 here because it is greater than, and 1 here because it is lesser than 1. So is this balanced? Let's check. 0, 0, 1 minus 1, 0. So it is balanced. So this tree is balanced. So this is the rotation of right left. Always remember to find the balance factor and start from the bottom node. Now we're gonna apply insertion on a right left. We're gonna apply insertion on a balanced tree, and let's see what rotation are we gonna do. So let's say we're gonna insert node okay, so now we're gonna insert, let's say we're gonna insert 80 and 90. So if we're gonna insert 80, we're gonna put 80 under the right of 70. So is the tree balanced? Let's check. 1, 2, 3. So 3 minus 1, 2. We have 1, so the tree is balanced. How about we're gonna insert 90? Okay. 90 is inserted. Let's check if it's still balanced. 1, 2, 3, 4. 1, 2. Obviously, the balance factor is 2. So this whole tree is not balanced. So what are we gonna do? So as you can see, we're gonna start evaluating at the bottom. So we have 0 here, 0 here, 0 here, 0 here. So okay, this is all of the leaves are okay. How about 80? We have 1 balance factor. So okay. How about 70? 70, we have 1, 1, 2. So, I mean 0, 1, 2. So 2 minus 0 is equals 2. So, so we have an unbalance here. So we're gonna rotate this first. We're gonna rotate it. So we're gonna rotate it. As you can see, it it falls. The nodes are all at the right. So we're gonna do a left rotation. We're gonna do a left rotation. So first, the new root is now 80 of the subtree. So 90 here, 70 here, and 50, 60, 40, 20, 10, 30. So I'm gonna minimize this. So after a left rotation, this one, we have this. So let's check if the tree is balanced. So we have from the right 1, 2, 3. We have 3 minus 1, 2, 2. So it is now balanced because we have a balance factor of 1. But let's check it node by node. So we have the leaf having 0 balance factor. 0. We have 1, 1, 1 minus 1. We have 0. 2 minus 1. We have 1, 0. We have 1, 2, 3 minus 1, 2. We have 1. So it is balanced. So that is all, guys, for my part. I'm gonna pass you over to Kenneth to show you the source code of an AVL tree. Thank you.
So, well, good day. Well, for me, it's actually a very early day right now. It's 3 a.m. So, at this part of the video, you're probably already asking yourself, so how would this look like in code? Well, this is it. And don't worry, we will provide the code with you alongside with the video. I'll probably post this in a repository and hand this over to you guys. Or put it in the description, whichever is more comfortable. So we're gonna dive straight in. So first we gotta make obviously the structure for the AVL tree node. So first is the key, and then the pointer towards the left and the pointer towards the right. Similar to a linked list, which has a double linked list or double A linked list, which has a head or a tail. And then this time there's a second also information on it, the node, which is the height of the specific node. Be it is it a leaf, a root, something else, maybe it's a trunk, who knows? Any other part of a tree that I could say. Okay, maybe it's too late for jokes. But so let's dive straight into the functionality of the let's see. Here. Function to create a new node. let's use this one. So obviously we need to use malloc, as our teacher has already taught us, because memory overflow, and it will cause a big bottleneck. So we need to memory allocate the specific amount of memory that is necessary or needed for that specific value, be it an integer or character. But in this instance, it is an integer. So yeah. So now we set the key of the node, with the node pointing to the key as the key being inputted. So for example, we put the key as 10. So then node will now, the current node that we're talking about in this function will now be whatever value that we inputted, and then it will now be pointing to null and towards the left, and then also pointing to null towards the right, and then its height will be 1, because a new node is initially added at leaf. So be it the very first node that we ever put, its height will be 1. And then return the node, because this node is now completely built. But don't worry, we will come back to this as to, so what about the node left, right? Choo 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 choo. Okay, don't worry. So, wait, let's skip the right rotation and the left rotation. So, I'm pretty sure you're all familiar with the structure of an AVL tree, right? Well, I know you guys won't reply to me. You guys are probably sitting comfortably at home. But this is what an AVL tree looks like. Three, there are the 30s on top, 20, 10, 25, 40, and 50. Could you say that this tree is balanced? Well, it has to be. Because if it's not, then it would probably not look like this. Well, as what Bral and John would have probably discussed to you already, there is a way to determine the balance of this, which we will get into right now. But before that, I'm gonna just tell you guys about this program. This program will first allow inserts of whatever value you want. So in this instance, I put 10, 20, 30, 40, 50, and 25, which created this AVL tree. As to how it created this AVL tree, once again, we will go into it in a fair bit. But let me just continue along so for a bit. Now, it will also talk about pre-order, in-order, and post-order, because this was one of our previous topics, and I just wanted to highlight how it would look like through the AVL tree. And then also a delete node, which was part of the requirements in an AVL tree as to deleting one of the nodes. So in this case, I deleted 20. So now, yeah, okay. So that's delete node, and then an insert 60 once again. Okay. Let's see. Yes. Wait, don't worry about this. This is filler. I was testing something there. Okay, so this is basically everything you need to worry about: deletion, and pre-order, in-order, and post-order. This is mainly what you have to focus about. And yeah, also I just chose to do pre-order for the after deleted node. Although I could print it like this into the terminal, I feel like I was very time constrained in doing so. So let's not dive into how I formulated the pre-order traversal, in-order traversal, and the post-order traversal. For now, we'll talk about that in a fair bit. This part of the code is actually for the deletion. Deletion, if I am correct. Yep, here, delete node. This is for delete node. And then this one is for the minimal value. And then this is for insertion. Yes, right here. So we'll now go into insertion. So before we get to insertion, I mean no, we're already insertion. Sorry. So we're now in insertion. So remember, an AVL tree is basically a binary tree with extra steps. With extra steps, meaning that it can shift around as if it's a snake slash a worm slash like I don't know, a tree that roots move a lot apparently. So we perform first the normal BST insertions as the previous group has already told us how to do. So I'm pretty sure I don't need to explain this, but I will do a short recap on set. So if node is equals to null, then return the new node key. aka just return back the original value, and then after that call this function. If key is less than the node pointing to the key, okay, it's not equals, the node to the left is equals to insert. This is recursion. And then after that, else if key is greater than node towards key, then node to the right is equals to insert node to right key. This is basically just making sure that the BST is set as normal. So, meron siyang nagbalik-balik. These two are insertions. So anyways, else equals keys are not allowed in BSTs. Return note. This is just the baseline if delegate marks up because something is wrong. This is error finding. In JavaScript you could call this catch, I believe so. Yes. Now update the height of the answer sister node. Cause remember, we did tinker with the nodes a fair bit here, so we just need to update the height. Now get the balance factor to check if the node becomes unbalanced. Now remember, I vaguely remember it being in the script that John will talk about the how to get the balance factor. So I'll just touch a bit also about that. I believe I put it here. Yes, here. I believe John also talked about this, that it is node left minus node right, but also that sometimes it can be the other way around. It doesn't necessarily matter. You just need to find the difference. Now, I do believe that I don't need to explain what the balance factor is for anymore. If you've listened to Bryle's 1 hour long video, you probably understand. Okay, now, after getting the balance factor, because you are returning the node into here, get balance factor. If node is equals to null, then return 0. This is once again, this is just a case in case it is a, what do you call that? The node is empty, or the node is pointing to the node you put is like, for example, null. Then yeah, okay. Let's see, where were we? Here. If node becomes unbalanced, there are 4 cases. So if it is unbalanced, so remember there are only 3 cases where it's okay. So that's 0, 1, and -1. So these are all cases where it's not that. So left case, right case, left right case, and right left case. I I also remember Bryle and John talking about how this works. So I will not touch on it too deeply because that will add onto the very long time that this video is already in. So I'll just talk about how this works. So as they said that left case is when the balance is greater than 1 and the key is less than the node key. This is just for safety reasons. Yeah. Now we need to do a right rotate because the left is unbalanced. There's too much stuff towards the left. So we need to rotate the tree to the right. So let's see how we do that actually. So I believe I put that right here. Okay. So struct node x is equals to y points to the left, and struct node temp2 is equals to x points to the right. Now this is technically just declaration of what these could be. Now to perform the rotation, um, similar to how you would do, let's say, a is equals to b choo 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 choo. Like how you would transfer the value of an item using pointers. This is basically the same thing, right? So you're using a temporary value, which is x, and then after that you are going to rotate it. So you're using t2 to store x pointing towards the right, which, yeah, in this case should be whatever is the right of y to the left. So now y to the right is equals to y, and y to the left is equals to t2, which made it rotate towards the right. So now if if you were to look back at one of John's example, this is the point where I believe x would now become the center point. So it would now be like, wait, is it like that? Yes, yeah. So for example, 10. So 10 would now be, and then let's say this was, say 25. Okay, 24. 24 and let's say 25 there. 24 and 25. This will now be x, and then this is your y. Since your y is x to the right, this is now your y. And then your left. So updating the heights to the current thing, because after all, you need to continuously update the height. Now, this is the point where I must remind that all of this is moving in linear time. So believe that all of this is in OV1. Yes. OV1. Forgive me if I'm wrong though. Okay, so return new root. So whatever is the new root. So whatever was the top portion, which is 10 in this scenario, but this is just a hypothetical scenario in this case. So it's the same thing with the left, but rather than um, we used x, we used y, and y to the left, and then x. So basically the same thing, but then you change. So it would rather look like this. Um, Remember that this is the case when you turn to the left. It's usually because there's too many items towards the right, so then you rotate to the left so that it becomes balanced once again. So let's say that's 10, that's 20, that's 30. We need to make sure that 10 becomes the left side of 20. So we need to change whatever is there. So after performing the rotation, it should look like this. Yes. And then updating the heights once again, and then returning the new root, which is 20. Okay. Now there are other cases, right? Left right case and the right left case. And it's basically also the same thing, Rasad. So if left right case, the balance must be greater than 1, and then the same security key as well. Just making sure. And then node to the left is gonna be equals to left rotate whatever is gonna be returned by this. And then after that, return right rotate node. So it's gonna rotate Nasad with the node. So unfortunately I can't draw that much right now. So you're just gonna have to base it off John's diagrams. But this is how you would do it for left right case and right left case. And I believe that's it for insertion. I believe so. Yeah, that's everything. So now we move on to delete node. So delete node is also remember the delete node is also similar to how you would delete it as a binary tree. So the same thing, check if the root is equals to null. If it is, then there's no point. It's already null. What is there to delete? So remember, deleting a node does not necessarily delete, like, to get rid of the information, but the just to make the pointers before it, so whatever's pointing towards it, null. But the tricky thing is, since it's a tree, you need to make sure that all of its children are left behind and transferred over to the parents of that node that you're trying to delete. So how would you do that? So this let's do the scenario where only one child or no child. If root left is equals to null and right is equals to null, so the scenario where there is no children, then there is, yeah, then you perform this. I forgot what this does. Node this was a node if okay. we'll go we'll go back to that later. And no child case. If temp is equals to null, temp is equals to root, and root is equals to null. Else one child case, and then free temp because temp right now holds the root, and you want to basically erase it. And yeah, basically the same as how you would get rid of it when it's a binary, yeah, a BST, a binary tree. And this is the same thing. If the tree had only one node, then return. And then second, update the height of the current node. Now remember, everything's now switched up because you erased that one, so then everyone's height is now kind of different. Now get the balance factor to check if the node became unbalanced. Now at this point, because you erased it, and then it might have gotten like skewed to the left or towards the right because you got rid of the root. Needing to check Napod Sad and do the rotations, left left case, left right case, right case, right 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 left case. So the same thing as what we did sa insertion over here. Yeah. Um, I believe that is all that is necessary to talk about. Most of the stuff did get talked by Bryle and John already. And once again, the PPT and also this code will be sent over with all of the comments and stuff. Don't worry. Should I discuss this? This basically, okay, like a short description of this is basically, you know how pre-order is from root to left to right, in order is from left to root to right, post order is from root, wait, root na noon, from left, right, and then root. Um, this just uses recursion to show where you are already. I like to show like it's gonna display the root, which is for an example in this one pre-order 30 ang una because root man sa in pre-order root is first, so you print first the root and then you move to the left, which is 20. Move the put to the left, 10, and yeah, that's basically it. So let's just ignore this part lang. So I believe that's it. Um, if there's any questions, you can always refer to the slides or refer to the code itself. There might be a more comprehensive guide you could follow and code that is probably much more understanding, but from my perspective and from how I created this and how I saw this, this is as easy as it gets for me at least. I don't know about you guys. And that's it. Thank you so much.